I will begin. Dear Father, we thank you for this day. Again, I thank you for this class and these students. Just ask that you to, again, just help us to understand the material, and just pray that you would be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I hope you guys have a better understanding of like Graham-Schmidt and orthogonalization and all that after doing that assignment there. I should hope to have the solution posted like a little bit later today, if all goes as I hope. Do you guys have any questions about anything before I talk about the material? So the one that I've asked you guys to turn in Thursday, there's really sort of two topics on that. The one is concerns inner product space, which is totally new. We'll just talk about that today. It's not a big deal, but it's really an outlier for this course. All right. And then the other one is much more mechanical. Like the first problem is very mechanical. I think I forgot to print those out for you guys. I'm sorry. I was going to print those out and bring them to class. Rats. I will try to go print them out at the end of class if you can hang around. And I'll leave a stack like on a chair in my office if you want to come get it when you can, all right? So, because I think I said an announcement, there are actually two surprise attack missions due Thursday, right? Like the one is one I wrote last week, and the other one well, actually I forget when I wrote them, but we'll look at them together towards the end of class. How about that, all right? Okay, so but the two topics on the one that's due Thursday that I posted the latest one I posted, really two problems. The one is concerning the spectral theorem, which we've talked about before a bit, but this is kind of like a reverse engineering problem. So I want to show you guys something. Like the spectral theorem essentially is this, is if A transpose is equal to A, then there exists an orthonormal eigenbasis. So you got your V1, V2, Vn, right, equals to beta, where, how's it work? Beta transpose A beta gives you what? Gives you diagonal matrix, right, D, where you got the eigenvalues down the diagonal, right? That's the real spectral theorem as I've presented it to you guys. This marker's trash. It's a bad season for markers right now. I tell you what. Anyway, with chalk, you know what you got. You know what you're getting into with chalk. Like you hold it in your hand, you look at it. There's no doubt what the chalk is going to do, right? But a marker, it's anybody's guess. So that's like, this is one aspect of it, but there's a kind of a reverse engineering aspect as well, which is that I can actually write A as, I think this is actually generally true, but we can write it like this. It's like V1 transpose plus lambda 2 V2 transpose plus plus lambda n Vn transpose, right? Like that's actually a formula for A. You can build A from the eigenbasis like this. I don't think I told you guys this before, but that's one of the problems, is exploring this idea for a specific set of three orthonormal vectors. All right. Here, let me show you how this works in 2 dimensions. It's easier there. We could do like V1 is, let's say 1, 3. That's like what? 1 over the square root of what? To normalize it, what do I need here? Square root of 10. Great. And then what's my V2 got to be if I'm looking for an orthonormal eigenbasis? I mean, orthonormal basis for R2. got to be perpendicular to this. I got to do what? I got to flip the 3 and the 1, right? You got two choices. I'll put the 3 here and the -1 down there. If I do that, then the dot product of this guy and that guy are 0. They're perpendicular, right? This is my standard trick. Now you're like, well, why did you do that? Why didn't you put the minus on the 3 and the plus on the 1? It's just a choice. All right, there's two choices. I made one. I got to normalize it though. So I do what? Divide by square root of 10. All right, great. So I think in the problem I introduced like a big E. Like I say E1, something like this. E1 is V1 transpose, right? So like here, that would be, there's a square root of 10 in both of those, right? So we get a square root of 10 squared, so we just get a tenth, yeah? 1/10. And then we've got 1/3 times 3, 1. I'm going to read 1/3 rather. So my E1 matrix would be like 1/10, and that's going to give me 1/3 and then 3, 9. And I can also build E2. All right, same way. E2 I would build as V1, listen to me, V2 transpose, which is going to be 1/10, 3 minus 1 times, well, 3 minus 1 is a row vector. All right, so that gives me 1/10, 9 minus 3 minus 3, 1. My claim is that you can use these matrices to build a 2 by 2 matrix with any eigenvalues you like. So like, check it out. Let's try to build a, so you guys, I like eigenvalues that make the fractions go away, all right? Since I got tenths here, let me suggest an eigenvalue of 10. I like that. So 10 E1, and how about plus 20 E2, right? If I do that, my matrix is going to be, so that's 1, 3, 3, 9, plus 2 times 9 minus 3 minus 3, 1. All right, what's that give me? One plus 18 is 19. 3 minus 6 minus 3. And 3 minus 6 is minus 3. And 9 minus 2 is 7. Plus 2. Oh, that's good, because this didn't make sense. I was about to say the trace of this matrix is 26, which is what it should be, right? Because 10 plus 20 is that the eigenvalues are 10 and 20, I'm claiming. And, you know, the trace of this matrix is 26, and 26 is 10 plus 20, except it's not. And thank you, because 9 plus 2 is 11. What's 11 plus 19? 30, not an accident, because I'm telling you the eigenvalues of this matrix we just constructed are in fact 10 and 20. But it's better than that. Check it out. A times V1, what do you think we get? What's A times V2? What do we get? You work it out. What you're going to get is you're going to get 10 V1 and you're going to get 20 V2, okay? That happens. And that has to happen from the formula, right? Like, think about this formula right here in the abstract, right? What happens when you take this formula, right? And you multiply it by like Vj, what happens there? What is what's V1, like what's VI transpose times VJ? What is that? That is the dot product of VI and VJ, right? And we're assuming orthonormal basis, so that's the Kronecker delta IJ. So what that does when you take this multiplication is it selects just the jth one. And you're left with lambda sub j, Vj, Vj transpose, Vj. Of course, this is just 1, and so that gives you lambda j Vj, which is what I'm claiming, is that when you multiply the matrix constructed like this by the eigenvectors you've used to construct it, they're in fact eigenvectors with the eigenvalues of your choosing. So this is a way of reverse engineering a matrix such that a given orthonormal basis will be the eigenvectors and have the eigenvalues you want. We don't often talk about reverse engineering in here, but there it is. That's like how we could build a matrix with an eigenvalue. Almost always we ask the students the other direction of the question, right? Given a matrix, how do you find its eigenvalues and its eigenvectors? But I think it's interesting to think about the other direction sometimes. So anyway, this is another aspect of the spectral theorem, is that you can decompose the matrix into a sum of these so-called projection matrices. These projection matrices, what they do is they project onto the eigenspaces corresponding to the problem. Like the range of E1 is the span of V1, the range of E2 is the span of V2. Anyway, I shut up. Enough about that. So that was the one problem. The other question's about inner product space, and that is another discussion altogether. Inner product space. So inner product spaces takes us finally out of the realm of column vectors. At last, we can talk at least a little bit in here, and not too long, but just a little bit, about the concept of an abstract vector space. What is an abstract vector space? All right? So we have to start with that. What is an abstract vector space? So we say V is a vector space. That's vector space over F. So this is a field. All right. If you have an addition, which goes from the cross product of the vector space, Cartesian product of the vector space itself back to the vectors, and multiplication, which gives you a way to take a scalar paired with a vector and give you back a vector. Like specifically, we take x comma y and we map it to x plus y. This scalar multiplication takes a constant and a vector and it maps it to c dot x. So this is called vector addition. And this is called scalar multiplication. All right? And what's a field? Well, a field is a set of numbers where every non-zero number has a multiplicative inverse. So every non-zero number has a multiplicative inverse. This is what it means to have a field. So the field, basically there are three examples that you maybe are familiar with. You could have the reals. You could have the complex numbers, right? And if you're a little bit more adventurous, you could even use the rational numbers. And you could talk about a vector space over the rational numbers. In each one of these worlds, you're only allowed to multiply by the scalars in your field. All right, so like a real vector space, when we talk about a linear combination in a real vector space, we're talking about real linear combinations. Talk about a linear combination in a complex vector space, we're talking about complex linear combinations. When we talk about linear combinations in a rational vector space, we're talking about rational linear combinations. But all those three sets of numbers are such that every non-zero one of those has a multiplicative inverse. Something that's not a field, for example, would be integers, right? Z, not a field. Why? 2 is in the integers, right? But 1/2 is not an integer. It's like Z is not a field. If you wanted to work with something like a vector space over the integers, you'd have to work with something a little bit more esoteric. It's called a module. I'll be teaching students about modules next semester in Math 422, for example. But it's harder than what we're doing in here, because if you're not working over a field, not everything has a multiplicative inverse, and that like severely handicaps many of our arguments, because we divide by numbers willy-nilly left and right? And if you can't do that, it spoils a bunch of our arguments. So this is what a vector space is in the abstract. Now, what are examples? So we're not talking about just column vectors anymore. Here's some examples of vector spaces, just to give you a sense of how weird this is. Well, first of all, let's not be weird. The first thing is Rn. Rn is a real vector space. And I'll keep it real. All over the reals, all right? Because you can add vectors and you can scalar multiply vectors, right? We know that. In fact, this is the quintessential vector space. It's just Rn. This is everything we've done this semester almost without exception, right? The other example, though, is matrices. M by n matrices form a vector space. In this way of thinking, every matrix is a vector. Right? That obviously is not the language we've used this semester, right? For us, a vector is a column vector. I sometimes call those a concrete vector in the larger discourse. But in this abstract way of thinking, a matrix is a vector because I can add two matrices and get another matrix, and I can scalar multiply a matrix and get another matrix. And it satisfies the axioms of a vector space, which I will not burden you with, right? We don't want to be burdened with what has been. We know that. So 3, you could look at polynomials. The set of all polynomials is a vector space because you can add two polynomials together, and what do you get? A polynomial, exactly. And what happens when you multiply a polynomial by a number? You get a polynomial, right? That's a vector space. Let's get weirder, though. You could look at the set of continuous functions from the reals to the reals. Continuous functions from the reals to the reals. This is a vector space because the sum of continuous functions is what? Remember from Calculus 1? By the limit laws, the sum of continuous functions is continuous. And a scalar multiple of a continuous function is continuous. So, with respect to the natural addition of functions, the set of continuous functions forms a vector space. All right? And you could do fancier stuff. Like you could look at the set of smooth functions, C infinity, from the reals to the reals. Smooth functions. What's that mean? That means you can take as many derivatives as you want, right? Well, the thing is, if you have one function, you can take as many derivatives as you want, and you have another function, you can take as many derivatives as you want. You add those together, guess what? You get another function that you can take as many derivatives as you want. So the sum of smooth functions is smooth, and the scalar multiple of smooth functions is smooth. All right. It gets weirder. If we talk about functions from a set to V being a real vector space, set, real vector space. This is a vector space. The set I'm taking as the domain for the functions, it doesn't even have to have a notion of addition. It could be a set of cats, for example, if you wanted to look at functions with evil domain. The important thing is you would define f plus g of p would be equal to f of p plus g of p, and a constant times f of p would just be equal to c times f of p, and you do this for all p in the set, for all cats or whatever, dogs, whatever you want your set to have. Those pointwise addition and scalar multiplication rules define a vector space. So the possibilities are endless. My point is, as long as we can define a way of adding things and scalar multiplying things, it's a vector space. Now, some of these vector spaces are somewhat familiar, right, to our experience so far, because they're actually finite dimensional. Yeah? They're finite dimensional vector spaces. Only 2 on this list are finite dimensional, right? To be finite dimensional means that you can find a linearly independent spanning set. We've talked about this, right? A basis is a linearly independent spanning set. Yeah? And like, what's the basis for Rn? Well, we know it's the span of what? E1, E2, En, right? That's the standard basis. How many things are there? N, right? The dimension of Rn is n. It's n-dimensional. I'm saying this to you because something happened in my linear algebra class last class. I asked them this question, like essentially what the dimension was of Rn, and they didn't know. And this disturbed me to my core. So I'm telling you now, so that if you take it with Dr. Majerick next semester, you will know when he asks what the dimension of Rn is. You will tell him without flinching. You will say with authority, n, sir, it's n. Very good. All right, we got it? Now, this right here is the span of Eij, such that 1 less than or equal to I comma j, well, 1 is less than or equal to I, less than or equal to m, 1 less than or equal to j, less than or equal to n. N is in nanu nanu, m as in mommy, right? Those are the matrices which have 1 in the ijth spot and 0 elsewhere. How many of those are there? For an m by n matrix, we have m times n components. What's the dimension of Rmn? What's the number of these guys? It's the number of components. How many components in an m by n matrix? Simply m times n, right? So there you go. So the examples 1 and 2 are finite dimensional, but the others are what we would call an infinite dimensional space because there doesn't exist a finite basis, right? Like I can write down a basis for the polynomials. What's a basis, you know, for R of x? Sometimes we also call this like P. P of x, you might call it polynomials in x. So like a typical thing in here looks like a0 plus a1x plus a2x squared plus da 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 da, right? Plus, well, it has some order, x to the n, right? Degree n. That's a typical element of the polynomial, right? That's a degree n polynomial. So can you guys tell me what's a basis for the set of polynomials? Now this is taking us outside of what we've proved this semester, right? We have, you know, dipped our toes in a much deeper pond this last 15 minutes. And don't worry, I'm not going to push you in. Like, I have a token example you're going to do. You're going to do the most interesting part of the calculational ensemble of the next semester, which I almost never ask them to do there anymore. Oops. But look, isn't it pretty clear that if f of x is this, then f of x is an element of the span of what set? Isn't it just 1, x, x squared, x cubed? We'll be here all day, right? It's endless. The set of, this is the so-called monomial basis. The monomial basis, you know, for the polynomial space. How many things are in the monomial basis? Infinitely many. What kind of infinity? Do you guys know about kinds of infinity? Countable, right. So this one has, the size of this basis is the size of the natural numbers. So this is a countably infinite vector space over the reals. They're also uncountably infinite. So like the dimension of a vector space in the infinite dimensional context is defined to be the cardinality of the basis. So like the smooth functions, they're bigger than this. There's a lot more in there. Okay, so that's just a snapshot of like what we study in Math 321. We study abstract vector spaces And we also study like linear transformations from one abstract vector space to another, right? That's the playground in which we're playing in Math 321. So what's one of the more interesting things we've done in here is talk about the angle between vectors, right? We talked about the length of a vector, and how did we do that? Definition, right? We had like the length of x for us is what, like the square root of x dot x, right? And the angle between x and y, how was that defined? It's like inverse cosine of x dot y, right, divided by the length of x times the length of y. This is, you know, for x comma y in Rn, right? And of course, for this one, we better assume they're both non-zero, right? We can't calculate the angle between the zero vector and another one, right? So the abstraction of this concept of dot product is called the inner product. So an inner product, it has to satisfy a few axioms, like the inner product of x plus y with z is inner product of x with z plus the inner product of like y with z. You have to be able to pull scalars out, like the inner product of cx with y is c times the inner product of x with y. I'll keep it real. All right, we actually study this, the complex generalization of this in Math 321 typically, but if we're real, it also has to be like symmetric. So like the inner product of x with y is equal to the inner product of y with x. And last but not least, you have to have that the inner product of x with x is greater than or equal to 0. And the inner product of x with x equals to 0 implies x is equal to 0. All right. So these are some of this is like the DNA, if you will, the axioms of an inner product. And once we have an inner product, we can build a norm. We can build a sense of length. What's the length of a vector in an inner product space? Well, it's the square root of the inner product of x with itself. So this whole concept is all modeled over what we've already done with the dot product. See, the length of a vector with the dot product is the square root of the dot product of the vector with itself. The length of a vector in an inner product space is the square root of the inner product of x with itself. So basically, we're abstracting the dot product to something we're calling an inner product. All right? So what are inner products? Like, let me show you the inner products that we can define. Here. Any questions before I blather on? Yeah. So of course, first order of business, the dot product is an inner product. All right? We talked about that one this semester already. For polynomials, we can define the inner product of f of x and g of x is equal to the integral from -1 to 1 of f of x times g of x dx. This will define an inner product. You can check, it's somewhat evident that it will satisfy my axioms, right? Like certainly it's linear in the first slot because the integral is linear and the formula that I wrote down inside the integral plays nicely with what I'm claiming. Right? You can pull a constant out of an integral, so that's going to give us like axiom 2, right? Can you guys see, well obviously it's symmetric, right? Can you guys see why it would be, like let's think about the fourth axiom just a second here, just to kind of process this. Why would that be true? what would like the inner product of a polynomial with itself? That would be the integral from -1 to 1 of f of x quantity squared, right? Think about that. We're integrating a quantity which is what? So f of x squared, right? We can tell about that. It's non-negative, right? It's greater than or equal to 0. It's also continuous, right? Which means that if it's non-zero at one point, it has to be non-zero everywhere else near that point. So if you think about the integration process, the fact that it's continuous and it's non-zero, right? We cannot have a place where it's, non-zero and not have that lead to this being anything it can't be zero. The result cannot be 0 if f of x is non-zero at even one point. Let me say it that way. If f of x is non-zero at even one point, it has to be non-zero. The square of f of x has to be non-negative at points close to that one point. Consequently, the integral would be non-zero. So if this integral is 0, it's proof positive that f of x is the 0 function, the 0 polynomial. And that essentially is the argument to get like number 4 here. Notice that I'm using f of x in the place of x. Okay, this is like I'm making a substitution in terms of concept here. If you don't, I hope you can track my notation. Like here, x, y, and z, they're abstract vectors. So they could be polynomials, they could be matrices, all right? So that's the inner product on polynomials, all right? So like, for example, if we calculate the inner product of, 1 with itself, what do we get? What's the integral of 1 from -1 to 1? 2, all right? So this tells me that the length of the constant function 1 in polynomial space with respect to the given inner product here is what? The length of 1 with respect to this choice of inner product is the square root of 2 in this world. What's the length of x? Right? Can we calculate that? You guys tell me, what's the length of x? So what's the inner product of x with itself is what we have to ask, right? So that's the integral from -1 to 1 of x times x, which is x squared dx. Lo and behold, we've got x cubed over 3, evaluated from -1 to 1, also known as 1/3 minus a minus 1/3, which is 2/3. So you see the length of the polynomial x with respect to this choice of inner product is the square root of 2/3. Now I keep saying with respect to this choice of inner product because the surprise attack mission I gave for you guys to do Thursday, I've defined the inner product on polynomials differently. In the one I gave you guys to work out for Thursday, instead of integrating from -1 to 1, I just have an integral from 0 to 1. The truth of the matter is you could pick any domain you liked, and that would be a suitable inner product for the polynomials. This one is standard for reasons connected to mathematical physics. This has to do with what are called Legendre polynomials, which appear naturally in the potential formulation of electrostatics, right? Like there's this beautiful thing called the multipole expansion where those Legendre polynomials appear in like a really natural way. One is one's not a Legendre polynomial. If I wanted to normalize one, what would I do? One is not a unit vector, but what would be a unit vector here in this world? That's right. 1 over the square root of 2 has length 1. So this right here is a unit vector with respect to our wild new madcap inner product here. that we've defined. The length of x is the square root of 2 over 3. That's weird, right? Are these perpendicular? Is 1 and x perpendicular? What do you guys think? What would it mean for 1 and x to be perpendicular? Same definitions we've always had, right? Every place we did dot product before, now do inner product. Two vectors are perpendicular if their inner product is 0. Is the inner product of x and 1 0? We got what? Integral from minus 1 to 1 of x dx. This is an odd function integrated about a symmetric interval of the origin, and as such it's 0. Of course, you could do the calculation, x squared over 2. Evaluate from minus 1 to 1, 0. So x is perpendicular to 1 in this wacky world. That would not be true for your homework problem, because there you're integrating from 0 to 1, and the integral of x times 1 from 0 to 1 would not be 0. It would be a half. So like x and 1 would not be perpendicular if we put a 0 here and a 1 here. All right? Yeah, this is a definition. Yeah, like I said, they're, from our perspective, at the moment arbitrary, but they're really not arbitrary as they arise from problems of mathematical physics, for example. For this class, they're given. At the moment, I'm giving them to you as minus 1 to 1. So guys, let's think about this. For quadratic polynomials, we can complete this thought, right? We could find an orthonormal basis for quadratic polynomials with respect to this inner product, right? Look, we've already done, I think, 2 of the things. We found that if we so like P2, quadratic polynomials, what's the basis? Let me state the problem over here more cleanly so you know what don't lose track of me here. Yowzers. So here's the task in front of us. Given that the inner product of f of x and g of x is defined by the integral from minus 1 to 1 of f of x, g of x dx, find orthonormal basis for span of 1, x, and x squared. All right? My point to you at the moment is that we've already done like some of this, because we just figured out that the length of 1 is the square root of 2, right? So let me start the answer up here, right? Like we got beta 1 over the square root of 2, right? That would be my typical notation v1 prime prime, right? If this is like, I can think of this as like v1 for Gram-Schmidt, v2 for Gram-Schmidt, v3 for Gram-Schmidt. You mean we can Gram-Schmidt here? Oh yeah, we can still do all that. Just we need to replace dot products with inner products, is all. How about, oh, but v2 is perpendicular to v1, isn't it? 1 and x are perpendicular. We just saw that. So if that's one of the things you should have picked up on, I hope, is that as we do, what's the purpose of Gram-Schmidt is to orthogonalize, right? So if you're given a list of vectors, and the first 2 of them is already orthogonal, Gram-Schmidt does nothing, right? All we need to do is normalize x. So the next vector, we already have everything we need over there. We can write that down. If x has length squared of 2 over 3, we just need to do like 1 over the square root of, what did I say? 2 over 3 times x, right? All right, so looks like we're still going to have to figure out like v3 prime. What's v3 prime going to be? It's going to be v3 minus, here we go, inner product of v1 prime with v3 divided by v1 prime, right? Times v1 prime minus the inner product of v2 prime with v3 divided by v2 prime, v2 prime, v2 prime. All right, now here I'm suggesting that v1 prime is just 1 and v2 prime is just x, okay? Now I would suggest that we go do these inner products, you know, off to the side, right? Let's do them. So like, what's v1, v3? Well, v1 prime, v3, fine. So we're talking about x, what was v3? Oh, I'm sorry, v1 was not x, was what? 1. It's 1. So 1 and x squared, right? So that by definition is what? That is the integral from minus 1 to 1 of 1 times x squared, right? Which is what? Well, that's 2/3, right? I don't know what it is. I can't do math. Yeah, x cubed over 3 evaluated from minus 1 to 1. So yeah, okay, 2/3. Yeah, 2/3. 2/3. All right. So we're going to have v3 was x squared minus the top. We've got 2/3 upstairs, right? What's v1 prime? V1 prime. 2. All right. So we got a 2 there. To be clear, what you did, v1 prime is the inner product of 1 and 1, which is the integral from minus 1 to 1 of 1 dx, which is equal to 2. That's why you knew it was 2. And also we did it on the other board, right? So, all right, but that has to be multiplied by v1 prime, which was what? Kind of boring, but 1, right? Great. What's v2, v2 prime, v3? v2 prime, v3. We've got x with x squared, I think, yeah? X with x squared, which is the integral from minus 1 to 1 of x cubed dx. That is 0. Well, that's wonderful. So actually we have 0 over, who cares, whatever v2 with v2 was. I guess that was 2/3. That was 2/3, but doesn't really matter because we got 0 in the numerator, right? Lo and behold, we've got x squared minus what? The Tuesday, yeah, minus 1/3, right? Now, if you have understood Gram-Schmidt for column vectors, this shouldn't be too mysterious. If you don't yet understand Gram-Schmidt for column vectors, you really, by rights, should be totally lost at the moment. If you're not, I'm impressed. But, okay, so great. Now the question is, I could put that up there, but we're looking for an orthonormal basis, right? So how do I normalize this? What do I have to do? Divide by its length. I mean, I have to calculate the length of this thing. What's the length of it? Right. So v3 prime with v3 prime equals the integral from minus 1 to 1, in this case of x squared minus 1/3 times x squared minus 1/3. All right, so what is that? That's the integral from minus 1 to 1 of x to the power 4 minus 2/3 x squared plus 1/9, I think. All right. And then this gives us like 2/5 minus 4/3 plus 2/9, which is whatever it is. Ah! Aw, man. Sorry, I took my calculator out earlier. I was up to some shenanigans for Calculus 3. There may have been a 67 this morning. Let's see here. 45ths maybe? Looks like a job of 18 minus 60 plus 10 divided by the 45, I think. Yeah. Oh, that feels wrong. Huh. Oh, when you integrate x squared, what happens? You get a third, right? Yeah. Is that the same as the third that's already there? No, these are different thirds. There's a 3 squared here, my friends. This is a 9, which is good because that makes this a 20, not a... All right. So now we got ourselves 1/15? 20... I got 28 minus 20. I think I got 8/45. So you can do 1 over the square root of 8/45, and then x squared minus a third. And there you go. That is an orthonormal basis with respect to our -1 to 1 inner product. So like your homework, I ask you to do the same thing, but not with respect to the inner product that goes from 0 to 1. All right. I ask you a little bit more than that, though. Let me show you. The rest I need pictures for, so we should look at the projector, yeah? These orthonormal bases on their lonesome are not that interesting. I think what they're really interesting for is for building projections onto subspaces. So one of the things we can do, now that we have this orthonormal basis to the quadratic polynomials, is we could do things like project the exponential function onto the quadratic polynomials, right? What would that look like? You're like, well, that's outside of the university that you're looking at. Well, fair enough, but let's expand my scope a bit and throw in the exponential function. You know, I can ask in the wider function space, what's the shadow of the exponential function onto the quadratic polynomials? I'll show you. So this is on page 273 of the notes. So first order of business, I have already done. I wanted to work out in class with you guys, since I asked you to do a problem like it. So we did that, right? Now that we have, so this is what we just found, right? We just found 1 over root 2. Notice that division by the square root of 2 over 3 is the same as multiplication by the square root of 3 halves, right? And likewise, square root of 8/45, all right? There you go. That is our orthonormal basis for the quadratic polynomials. These are actually the first 3 Legendre polynomials. So if I wanted to calculate the projection of the exponential function, right? If I wanted to calculate the projection of the exponential function into quadratic polynomials, I could just take basically dot products with this orthonormal basis. Well, I say dot products, but I really mean inner products, right? And so here's what that is, looks like. The inner product of the exponential function with v1 and v2, and so like, if I can make it slightly bigger here. Oopsie. So inner product of the exponential with v1 is like 1 over square root of 2, integrate e to the x from minus 1 to 1, right? And that's an integral we can do. It ends up giving you this, which is approximately 1.661, okay? If I integrate with the exponential against x times the square root of 3 over 2, I have this, which we can integrate by parts and get that. And lo and behold, it's about 0.901. I can calculate the length of the shadow of the exponential function in the v3 direction, like so. Inner product of f with v3. You know, and by the way, guys, for your homework, I don't expect to see details of the integration. You can use Wolfram Alpha or whatever. It's cool. This is not a Calculus 2 class. You got nothing to prove to me, all right? Although I do expect that you could at least integrate polynomials for the next test. That is true. I don't deny it. It's true. But you should be insulted if you think that I don't think you can do that anyway, right? Students don't seem to have this kind of animus against professors, as it turns out. But so that's 0.04. That. And so putting it all together, the projection onto the quadratic polynomials of the exponential function, 1.661 v1, 0.901 v2, plus 0.042 v3, which gives us this when you work out the arithmetic. So 1.03 plus 1.103x plus 0.017x squared. That's an approximation for the exponential on the quadratic polynomials. It's the closest one with respect to the notion of distance defined by the inner product here, right? Have you guys ever looked at an approximation for the exponential before? Calculus 2. How do we approximate the exponential? The Maclaurin expansion, right? Which is what? 1 plus x plus 1/2 x squared, right? This is a different approximation, obviously. It's kind of close though, right? We still got almost the 1 and almost the x, but this is pretty far away from what we do for the Maclaurin series. So it's a different approximation and it would serve a different purpose. Now, which approximation would be better? It depends on the context of your application, right? Okay. Another example, yep.
So instead of using e of x, e to the x, could you not just use a series approximation of that and then go through all of this?
Well, that would make it,
and then do it.
That would make it worse though, because then I'd have to calculate a series of integrals. I mean, I just have to integrate e to the x. It's not too bad, right? But yeah, you could always, I mean, this is something, once we know series, we can always replace what we have with a series and either make it better or worse depending on whether or not we're stuck. Here's another one. We can look at continuous functions from minus pi to pi. And it turns out that there's a nice set of functions like 1 cosine, sine, cosine 2 sine, cosine 2x, sine 2x. These are actually orthonormal. It's an orthonormal set of functions on this space. Well, that's not quite true, because when I take the inner product of cosine with cosine, I get the Kronecker delta mn with a pi. So that means that they have length square root of pi, right? So to fix that, I normalize by dividing by square root of pi here. But there you go. That's a orthonormal basis of trigonometric functions that we could use to approximate things on the set, approximate things that are like continuous functions or minus pi to pi, right? We can find the part of the function which lies in the direction of cosine or sine. Now, this isn't just an idle curiosity. This is actually the foundation of what's known as Fourier analysis. Fourier analysis is this crazy idea that you can build an arbitrary function as a sum of sines and cosines. This was the genius leap of Fourier in the early 19th century. When solving the heat equation, he simply proposed that after this thing, which we call separation of variables, which I think he invented, that, oh, well, you can just write the solution as a sum of sines and cosines. Any continuous function can be written as sine of sums and cosines, sum of sines and cosines, to which the rest of the mathematical community went, what? Really? No, man. And then they argued about it for like a half a century, but he was right. And in the process of like solving that and clarifying it, we invented much of modern analysis in that time period through the work of Cauchy, Weierstrass, others like that. But anyway, so like here is a discontinuous function. It's -1 from minus pi to 0, and it's 1 from 0 to pi, right? It's one of these deals, right? Step function. Right? This way, yeah. Just like that? Like that, yeah, okay. So, sorry, I'm an idiot. But then you can calculate the projection of that step function into the space of continuous functions using this trigonometric. Or you can at least project that function into the subspace spanned by the trigonometric functions, which it turns out is like pretty vast. And, well, you got to do these integrals, all right? You got to do these integrals, but they can be done. They're not that bad. And what you find then, this symbol right here means f of t is equal to this almost everywhere, which means that these two expressions differ on a set of measure 0, which you can learn about in our measure theory class, which we don't offer, except when students ask for it. And then we'll do it. You can talk to Dr. Schmidt. He knows things. He cares about these things pretty deeply. I know a little bit. But anyway, so this means it's equal almost everywhere. And in other words, you can build the step function from this infinite sum of sines. This is essentially what's behind MP3 music. MP3 music, among other, like compressing music into its fundamental pieces is like decomposing the music into its fundamental frequencies. And instead of remembering those frequencies as a blueprint for reassembling the music, it's a way of compressing data, audio data. That's like the way to do that. Visual compression works on other things like wavelet analysis and, well, other things, but like JPEGs or something totally different. But anyway, so this right here, what I've plotted is like, this is the lowest, I think. Just a sine is like the dumbest approximation to the square wave, right? But when then you add in the next term, you get closer. And then, yeah, the next one you get closer still. And as you go further and further and further out, you get closer and closer and closer to the square wave. However, there's always this like overshoot here, right? That's pretty like a standard feature. It's called Gibbs phenomena. It's kind of unavoidable, and you have to kind of like adjust for that if you're going to use these things. If you truncate them at finite order, that goes away in the limit. But when you truncate the Fourier expansion at a finite order, there's this Gibbs phenomena you have to kind of like deal with. Oh man, was that it? Am I out of stuff? Oops, come on. What's going on here? Ah, phew. Let me go back. The other thing I forgot to show you guys that I was going to tell you is this is like the length of matrices. This is like a totally different thing, but like the inner product of matrices, you just like, the inner product of matrix A and matrix B is just the sum over matching components multiplied. Just like the dot product of vectors is the sum over matching components multiplied, right? But the slick thing is that there's like a formula for the inner product of A and B. Do I have it written? Oh, I don't write a formula. I'm just showing it's symmetric. And so what the so-called Frobenius inner product for, do I eventually, oh, there it is, finally. Eventually, I confess that there's a super slick formula. The inner product of two matrices is actually the trace of A times B transpose. This is a sneaky way of writing out the sum of matching components multiplied.